My presentation is on coastal dead zones caused by nutrients, nitrogen and phosphorus, being carried to the sea and causing algae blooms that deplete oxygen from the water. Globally, there are around 500 dead zones. These are large areas almost completely devoid of life in coastal waters, typically where large rivers meet the sea. Most of these dead zones are concentrated along the more developed coasts of Europe, the United States, and China, but they occur on the coast of every continent except Antarctica. Worldwide, the largest source of nitrogen and phosphorus is from agriculture. Manure, fertilizer, and livestock waste are rich in nutrients. When it rains, runoff carries nutrients into nearby water bodies. These water bodies then, of course, eventually flow to the ocean. In China, there are approximately 14,000 CAFOs, which are concentrated animal feeding operations, and it is estimated that about 90% have no environmental controls whatsoever, and less than 10% have conducted any kind of environmental impact assessment. CAFOs alone in China contribute 40 times more nitrogen to waterways than industrial factories in the country. The CAFOs in China are directly blamed for a series of red tides that happened in the 1990s, and by the year 2000 cost the country $240 million in damages. Aquaculture is another significant source of nutrients, which is technically a field or branch of agriculture. Worldwide, aquaculture production has increased 600% between 1985 and 2005, from 8 million tons in 1985 to 48.2 million tons in 2005. 43% of the aquaculture production takes place in marine or estuary environments. Sources of nutrients from aquaculture include fish excrement, uneaten food, and other organic materials. In one study cited by the World Resources Institute, estimates are that for every ton of fish raised in aquaculture, between 42 and 66 kilograms of nitrogen is released, and between 7.2 and 10.5 kilograms of phosphorus is released. Just doing some simple math, that means that if only the 43% of aquaculture that takes place in marine environments is considered, then as much as 1.36 billion kilograms or 3 billion pounds of nitrogen and 2.2 million kilograms, which is 4.8 million pounds, of phosphorus are released into coastal waters worldwide. Nutrient pollution also comes from urban and rural wastewater discharges. This is somewhat less a problem in the United States than it is elsewhere in the world. In the US, 90% of urban sewage is treated, but in Europe, only 66% is treated. Asia, only 35%. Latin America and the Caribbean is at around 14%, and Africa is less than 1%. What this translates into is that sewage contributes 12% of nitrogen input into the streams of the United States, 25% in Western Europe, 33% in China, and in Korea, 68%. Developing countries have less than 35% of cities conducting any form of sewage treatment at all, and typically when treatment is conducted, it is only to remove solids. Overall, it is estimated that only about 20% of globally produced wastewater is properly treated. Combustion of fossil fuels is another source of nitrogen. Combustion releases nitrogen oxides, or NOx, a primary source of smog and acid rain, into the atmosphere. Atmospheric NOx falls back to the Earth during rain or snow events. The greatest contributors of NOx are coal-fired power plants and vehicle exhaust. Approximately 22 teragrams, and 1 teragram equals 1 billion kilograms, of nitrogen pollution is contributed globally each year from fossil fuel combustion, which is still only about 1/5 of the amount contributed from fertilizers. Okay, the cause of these dead zones is from eutrophication. Another name for these dead zones is hypoxic zones. Hypoxia is caused by a lack of dissolved oxygen in the water. When nutrients enter waterways, these nutrients are carried to the ocean, where they can be the catalyst for massive blooms of phytoplankton. Phytoplankton are photosynthetic organisms that live near the surface of the water using sunlight and other materials to produce their own food. Thus, they are primary producers. The conditions must be right for a bloom to occur. In addition to water temperature and salinity, iron, zinc, and manganese are required for blooms, but in fairly small amounts. The most important nutrients are nitrogen and phosphorus. Hypoxic zones develop when excessive nutrients are available, allowing the phytoplankton to multiply uncontrollably. There are creatures such as oysters, scallops, and sponges that filter some of the phytoplankton out of the water, and copepods, a type of crustacean, feed on it. But man-made inputs of nutrients means that blooms can be so massive that these creatures have relatively little effect in controlling it. Hypoxia happens at night when phytoplankton use more oxygen than they produce. This reduces the water's DO, and since blooms typically happen in warm water, this is occurring at a time when the water's ability to hold dissolved oxygen is already low. Another source of DO loss is when phytoplankton begins to die. The dead organic material falls to the bottom of the ocean where it is decomposed by bacteria. This decomposition process dramatically reduces the dissolved oxygen levels in the surrounding water, and in this scenario, a dead or hypoxic zone develops. And when these hypoxic zones develop, creatures either asphyxiate and die, or they swim away. Habitats that would normally be teeming with life essentially become biological deserts. Hypoxia is not the only effect of phytoplankton blooms. Other ecological effects can occur. If the nutrient source is steady, then blooms can become long-term events. Seagrass can die due to blooms that block out sunlight. Creatures need seagrass for forage and cover, and the death of the seagrass can lead to changes in fish and invertebrate populations. Another side effect of seagrass loss is that the ocean floor sediments are no longer held in place, so ocean currents can stir this material up and increase turbidity. One of the most infamous dead zones is in the Gulf of Mexico, near where the Mississippi River discharges into the Gulf. The dead zone is a yearly summer occurrence, and in 2015 it was measured by the National Oceanic and Atmospheric Administration at 6,474 square miles. It is the second largest dead zone in the world. Another famous dead zone in the United States that occurs every summer is in the Chesapeake Bay. Many years the dead zone encompasses as much as 40% of the bay. Nutrients in the bay have recently prompted the development of a TMDL for nitrogen and phosphorus for streams that drain into the bay. The increase in dead zones worldwide in recent decades has been swift. The number of dead zones scientists knew about in the 50s was around 42, but that number has been doubling every 10 years since the 1960s, and as of 2007 the number had reached about 500. Currently the largest dead zone in the world is in the Baltic Sea. Fortunately, this phenomenon of these oceanic dead zones is one that can be reversed. For example, the Black Sea used to hold the title of the world's largest dead zone, but by pure accident, the problem fixed itself. Between 1991, the year the Soviet Union collapsed, and 2001, the Black Sea dead zone largely disappeared. The reason is that following the Soviet collapse, Eastern European economies began to struggle and fertilizer became too expensive for the average farmer to purchase, and therefore nutrient loads were dramatically reduced. The Black Sea is now a major contributor to local economies through fishing. So in some ways the damage is not irreversible, but in some ways it is. According to the United Nations, the deterioration in water quality resulting from eutrophication is estimated to have already reduced biodiversity in rivers, lakes, and wetlands by about 1/3 globally, with the largest losses in China, Europe, Japan, South Asia, and Southern Africa. The goal is simple: keep nutrients on the land and out of rivers, and by extension coastal waters. But the solution is, of course, a bit more complicated. As discussed, there are a number of major sources of nutrients: agriculture, fossil fuel combustion, sewage discharges, but the area where the largest impact would be felt is reducing inputs from agriculture. According to an EPA nutrient management guidance document, the best approach to minimizing nutrient transport to surface and groundwater depends on whether the nutrient is dissolved in water or attached to soil particles. Dissolved nutrients require a reduction of the nutrient source and water runoff. This can be achieved by not over-fertilizing fields, i.e. apply fertilizer at rates necessary to achieve realistic crop yields, and apply the fertilizer at appropriate times of the year. Excess nutrients have a high potential to be transported to nearby waters. Similarly, fertilizing fields at appropriate times to maximize nutrient uptakes by crops will reduce the amount of excess nutrients available. Reduction of nutrients bound to soil particles requires adherence to sediment control BMPs, which is best management practices. There are two broad measures to achieve this: practices that minimize soil detachment and transport, and routing runoff to areas where the soil can be filtered or can settle out. Minimizing detachment and transport includes measures like maintaining vegetative cover on soils, minimize steepness of slopes near areas where nutrients are applied, maintaining a wide riparian buffer zone along streams, planting or leaving in place trees between fields to act as windbreaks, detritus cover on planting fields to absorb the energy of raindrops, which prevents them from dislodging exposed soil. Fortunately, these practices are relatively cheap to implement. They can be instituted in rich countries as well as poor with proper education programs. Coal-fired power plants and vehicle emissions are a little more difficult matter, though coal is in a slow decline in most places. Currently, China is the world's #1 user and producer of coal. They account for 48% of worldwide coal consumption and burn more coal than the United States, Europe, and Japan combined. There's still reason for optimism in China, though, as they are beginning to acknowledge the harm that so much coal combustion can cause. In 2014, China had a 1.6% reduction in consumption and has been periodically shutting down coal-fired power plants. Worldwide, since 2010, 2/3 of proposed construction of new coal-fired power plants were abandoned, and in 2014, the world added more power generation from wind than from coal. And worldwide, people are aware of the harm that burning coal can cause, and very slowly the world is moving away from coal for energy. And part of this is because the easy-to-get coal has been gotten, so they also need to find cheaper sources like natural gas. Urban sewage discharges are controllable sources of nutrients when money is available. Treatment capacity in high-income countries is about 70% of produced wastewater, while low-income treatment capacity is around 8%. Some countries, like India, for example, have wastewater treatment facilities in place, but 40% do not conform to operational standards, and due to lack of funds, many were abandoned and unused. There are a number of established ways to treat nutrients in wastewater, like ion exchange and biological denitrification, but they cost money. The UN recommends that countries be incentivized to construct centralized or decentralized wastewater treatment systems based on the needs of their particular situation. It is critical that these facilities are operated and maintained by trained personnel. The main thing to remember is that in many low-income countries, this will take time, as political structures, national priorities, socioeconomic conditions, cultural traits, financial resources, and so forth all vary. Countries need the flexibility to use a combination of treatment and non-treatment options over time and be allowed to progress and improve over time. It's not going to happen overnight. So, in conclusion, these massive hypoxic zones exist around the world due in large part to inefficient agricultural and aquaculture practices. Other activities, including fossil fuel combustion and wastewater discharges, contribute to the problem as well. These dead zones can be thousands of square miles in size and are the oceanic equivalent of a lifeless desert. They are caused by nutrient loading of inland waterways that travel to the coast and cause the formation of huge phytoplankton blooms that then block the sunlight and deplete water of dissolved oxygen. Creatures within these zones either flee or die. Solutions exist to combat the problem. The most readily available and cost-effective solutions revolve around agriculture, the largest contributor of nutrients. Fossil fuel combustion and wastewater discharges are more complex and expensive problems, but there are ways to reduce these sources as well. It is important to remember that reduction of nutrient pollution will not happen overnight. People need educated on reduction practices, and many countries will not immediately have the money or manpower readily available to institute changes immediately. There are some troubling trends that could work to sabotage some of the ability of reduction attempts to work. The world's population is growing rapidly. As a result, ever more intensive agriculture will need to be practiced to feed the booming population. Another problem is actually increasing economic growth. As economies in low income or developing countries increases, so too will consumption. This could spur an increase in fossil fuel usage, as these growing economies will need more energy, and over time, more and more people will purchase vehicles in these countries. So they would have more money to treat wastewater and use scrubbers and such to reduce inputs from coal-fired power plants, but the consumption needs of a growing economy may well more than offset the ability to institute these changes. So for the oceans, the problem is reversible, but any solution will take time and lots of money. Thank you, and these are my sources.